The next one is B, so that gets you 0, 1. The next one is C, that gets you 1, 1. The next one is D, that gets you 0, 0, 1, right? Now, basically, Huffman gives you this particular encoding of that song. That is fine. Technically, all of those still take 2 bits in general, and it is still the same amount of memory, but let's just look at this thing. So now, once I give you this particular encoding in order to play this song back to me, you would need to evaluate these bits, decode them back to their original values. So I need to get A, B, C, D from these set of bits and then play those notes to you, right? But that is fine because I know that A is 0, I get okay 0. Then I know that 0, 1, I get B. Then I get 1, 1, I get C. Then I get 0, 0, 1, I get D. But if you are a computer that has no idea what the original song is, you would first look at 0, okay. Then you also see 0, then you see a 1. So potentially that means that we have a 0, 0, 1. So that can potentially mean that we can either have for 0, 0, 1, we can either have the value D, that is the representation for D. So the first note could be D, or the first note could also be A and B, right? We don't know, and there is this ambiguity, right? So first note can either be 0, 0, 1, that is A, comma B, or the first note could also be D. So Huffman encoding needs to do 2 things. First thing is we need to reduce the amount of space required by using this frequency information, but we are going to use a variable length encoding. But now that gives us this problem that we need to know where a particular note ends, or we need to be sure that a particular note can be deciphered unambiguously. So there should not be any issues decoding this thing. As we see that there is an issue because 0, 0, 1 here could be AB, or it could also be D, right? So the main idea behind this encoding is we need to encode it as a prefix-free encoding system where no prefix of a particular note can be similar to another note, right? So what Huffman does is it creates a tree to represent all the notes. It uses this tree such that higher you go in the tree, you have the notes that have the most frequency. The lower you go down a tree, you have the notes with the lowest frequency. So essentially what it can do is represent A with 0, represent B with 100, represent C with 101, and represent D with 11. So now if you see the same note for A, B, C, D, and you represent it using this Huffman encoding, you get 0, 100, 101, and 11. Now, if you start decoding this particular notes sequence of notes from this set of bits, you first encounter 0. You look at all those encodings here and essentially say that we have a 0 prefix here, so that has to be a because no other symbol starts with 0. So you say we have a B, sorry, we have an A here. Now following that we have 1. So 1 can be either the prefix for B, C, or D. So you look at the next one. So you have 10. 10 can either be B or C. So again, there is still some ambiguity. You look at the next one and you have 100 that ends up being B, right? Similarly, for the next one, we have 1, then 0, then 1, that ends up being C. And finally, we have 1, then a 1, that has to be D, right? So that is how your Huffman encoding algorithm encodes this entire sequence into its corresponding bits. And those variable length encodings have to be different enough such that while you are reading them sequentially, there is no ambiguity between those encoding values. So what it does is it essentially creates a tree with respect to the frequency of those individual occurrences. So in this tree, remember, it creates this tree such that on the left hand side, you always go to 0. On the right hand side, you get a 1. Doesn't really matter, but essentially you see a 0, you say, ah, that must be A. On the other hand, you see a 1, okay, so then you say it is either B, C, or D. This entire subtree here, would have a frequency of 60, whereas this particular subtree here has a frequency of 70, right? So this particular right hand side of the subtree is represented by the prefix of value of 1, and then you check whether the next value is 0 or 1. If it is 0, then you go to this particular node here, and then you say it is either B or C, but depends on the next bit. But this entire subtree here now has a frequency of 23, and if it's the next one is again a 0, you finally end up with the value of B. So that is how Huffman encoding uses this tree structure to compress your entire song into a few as few bits as possible by leveraging the frequency count of that particular set of notes. Now note again that Huffman encoding also uses this frequency information to represent the most frequent note with as few bits as possible. So in this scenario, the most frequent note was A, so it just uses 1 bit to represent this thing. On the other hand, B and C had very few frequencies. So B had a frequency of 3, whereas C had a frequency of 20. So it uses the most number of bits, so that is 101 or 100, to represent, basically uses 3 bits to represent both B and C in its particular system. This guarantees that you are going to get the least amount of bits for your particular information. Secondly, this also guarantees that you're going to have unambiguous set of representations for all your notes. Okay. So if we use this particular representation for our previous song that we had for 50 minutes that had 130 million samples, we used 260 megabits to represent that particular song. If we now use this particular representation to store our song, our entire song now gets down to 213 megabits. That is basically a 17% improvement over our original raw bit representation, right? Okay. Any questions about Huffman encoding? Okay. So now let's look at the idea behind how we can actually construct this particular tree. So what we need to do is minimize the number of levels in our tree, right? So what we can do is basically pick the nodes that have the minimum most frequency and keep on joining them to create a new larger tree over time. So essentially the goal is the cost of the tree needs to be minimized, and what we want to do is minimize this entire cost such that except the root, all the other nodes have as few set of bit representations as possible with respect to their frequency, right? Okay, so come back to this thing, but so let's say that we have these set of nodes that has these set of frequencies f1, f2, f3, f4 all the way to fn. What we can do to represent this particular set of frequencies in this tree is pick the two frequencies that have the minimum most cost or the smallest frequencies, combine them, and basically create a root node where these two nodes are the children of this new node, where the new node would have a frequency of this f1 plus fj. Then once we have this new subtree, we continue this process again, considering this entire f1 plus f2 as a single node, and compare this with all the other frequencies, and we keep on creating this tree. So let's take this particular scenario here. Let me just okay, so let me just take this particular scenario where A had a frequency of 70, B had 3, C had 20, and D had 37, right? So in this scenario, we pick the two nodes that has the minimum most cost, that is B and C, 3 and 20. We combine them together to create a subtree that has B and C as children, and the root node has the total cost, that is 23. So now we have a new node, let's call it N, and that has a cost of 23, and we have removed B and 3 from the equation, right? So now we are looking at 23, 37, and 70. So out of these three set of frequencies, we see that 37 and 23 are the lowest. So we now combine N and D. So this particular set of nodes are combined. So we now get 23 and 37. That gets combined into a singular root node that gets the value of 60. And that basically, let's call it as N1 or N prime. And that gets us 60, right? So now we overlook B, C, D, and N, and we're only looking at 70 and 60 for A and N prime. So we combine those two to finally get the entire tree that we have here. So we start off with a bottom-up approach. We keep on combining nodes that have the minimum most frequency. And once we are done, we basically keep on and remove those nodes from consideration. We only use those root nodes to keep on combining back. So B and C gets combined to get 23. This 23 and D gets combined to get 60. Then this 60 and A gets combined to get the final set of frequency.
Why did we add A to the left rather than the right as we did when we found D?
It doesn't really matter. Either way works. It's just this is how the algorithm looks like. But essentially, if we wanted to add A to the right, then that is fine as well. Then this would be the 0 part of your subtree and A would be the 1 part of your subtree. You can go either way. This is just one example.
Okay, so then you could have A as 1 and then B would be
0, 1, 0. Yes. So A would be 1, B would be 0, 1, 1, C would be 0, 1, 0, and D would be 0, 0. Again, if you check, the prefixes are still distinctive enough to make us understand what the actual code is, and that is fine. And you end up with the same compression. Right, so for this particular scenario, A, B, C, D would be represented as 1, 0, 1, 1, 0, 1, 0, and 0, 0. Same thing, we see an 1, that is
Wouldn't B be 3 zeros if A went to the right at the very top? I'm making sure I understand. B, I didn't know if that would mess up the encoding.
No, you're right. That is, let me just check. So you are saying I need to bring up paint somewhere. Give me a sec.
Because I think I had some confusion with this the last time. I went over encoding.
Let me just draw it out. I'm going to draw it really. No, I can draw it properly. Okay, so let's say that we have B and C here, and then we have D here that is connected here. And then you want A to be connected somewhere here with this thing, where now we would have A here, this let's say is still D, and this is let's say still B, and this is let's say C. So in that scenario, A would be 1, B would be 0, 0, 0. Yep, you're right. C would be 0, 0, 1. And D would be 0, 1. Yep. Right. So in this particular scenario, if we are trying to represent ABCD, again we get 1, 0, 0, 0, 0, 0, 1, 0, 1. Right. Same number of bits, but again, still distinctive enough for us to figure out what the encoding is. So we get 1. Again, that is fine. We start off with this thing 0. Okay. I have 3 possible possibilities out of B, C, and D. We see the next one. Okay, now I have 2 possibilities, either B or C. We see the next one. Okay, that is definitely B. So 1 ends up being A.